I have lumped 7.2 and 7.3 together. We're continuing our work on probability. A spinner with 8 equally sized slices has 2 red, 3 blue, and 3 yellow slices. The dial is spun and stops on a slice at random. What is the probability that the dice stops on a red slice? So what could happen? We could get the first yellow, or the second yellow, or the third yellow, or the first blue, or the second blue, or the third blue, or the first red, or the second red. That's a 3, not a 2. That is our sample space. So probability is the number of times your event can happen divided by the number of items in the sample space. So this has a total of 8 options, and we want to know what is the probability of getting a red. So this would be 2 options out of 8, which is 1/4. Sometimes probability is just given as a percentage, or as a decimal, or as a percentage. So all of these answers mean the same thing. Okay, but it wants the answer in fraction form, so 1/4 is what it wants. Let's do another one. A bag has 6 marbles. What is the probability of drawing a blue? Well, there are 2 of them, so that would be 2 out of 6, which is just 1/3. Okay. A box contains 10 cards containing one of those letters. One card will be drawn at random, and there's an order to them. What is the probability of choosing a letter from N to Q? So it wants to know, I'm assuming it means including N and Q, not between N and Q. So there are 4 options there, and a total of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Oh, told me right there, 10 cards. So 4 out of 10 is my probability, which is 2/5. A coin is tossed 3 times. An outcome is represented by a string of the sort heads, tails, tails. The 8 outcomes are listed in the table. Note that each outcome has the same probability. So what that means is, what is the chance of getting TTH? That only happens 1 in every 8 tries. Why is it 8? Well, the first option has 2 possibilities. The second option also has 2, heads or tails. And the third one also has 2, for a total of 8. So, what is the likelihood of TTH? That would be 1 out of 8. Now, before we answer the rest of this, I want to show you my little device here. This is a normal curve approximator. If you take statistics, the entire class almost is based on the normal curve. So if I flip this down, these little ball bearings create a normal curve. And it's not perfect, but it's pretty close. See? That fills that curve pretty good. But my question is why? Why are there more in the middle than there are on the edges? Well, how do I get to this far right slot? What has to happen in order for me to get there? So when one of the balls falls, it's going to hit one of these little pegs, and at every peg it has to choose right or left. Correct? So how do you get to the far right? You choose right, and in theory, every single time. So if this is my normal curve full of all of those ball bearings, in order to get here, the only path is right, 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 right. I don't know how many there are. Something like that. Okay? Now, if you wanted to land in the middle, here's how you land in the middle. Right, left, right, left, right, left, right, left. Let's put one more in there. Okay? How likely is this? Very unlikely. How likely is that? Equally likely. Unlikely. Really? Straight R's is very improbable. But RL, 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 RL is equally improbable. Would you agree? The chance of getting exactly RL, 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 RL is very, very small. Just like the chance of getting R is equally small. Okay? So if that's the case, why are there more of these BBs in the middle than there are on the edges? Is this the only way to get to the far right? Yes. Is this the only way to land in the middle? No. How else could you do it? Good. So if we did right, right, left, left, right, right, left, left, that would do it. In general, what has to happen in order to land in the middle? You need an equal number of rights and an equal number of lefts. How many ways are there to do that? A lot. You could do 4 lefts and 4 rights, or 4 rights and 4 lefts, or a right and 4 lefts and then 3 rights. There are a ton of different ways to get there. And each one of these lines is not very likely to happen. But one of them has to happen, and the number of ways to end up in the middle is very high. Now, this is not perfect, right? Is the only way to get to the far right just taking rights? No, because sometimes the BBs bounce and skip a peg, like they'll bounce over, or sometimes they get kicked by other BBs because right there are hundreds of them falling all at the same time. So it's actually really, really messy, but the theory is sound. Essentially, to get to the far right, you have to turn right every single time, and that is just not likely to happen. Does it happen? Yeah. So in the latest one, it happened like 7 times. And while there are 7 on the far right, there are maybe several hundred in the middle column. Okay? So when we look at this problem, how likely is this to happen? 1 in every 8 tries. But how likely are you to get 2 tails? That's a different question, right? How many ways are there to get 2 T's? 1, 2, 3. So 3 out of every 8 tries, you will get at least 2 T's. Oh, 4. Sorry. You're a better counter than I am. So half the time, you're going to get 2 T's. Now, should I count this one? Should that count in the 2 T's? It depends on how you state it. If I said exactly 2 T's, would we count TTT? No. If I said at least 2 T's, would we count it? Yeah, so in probability, you have to pay very close attention to how the question is phrased. Okay, so this says, event A, go through and mark every time you have a head on each of the last 2 tosses. So does the first one count? No. A head in the last 2 tosses. So no, no, no. Here's a yes. No, 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 yes. What's the probability? 2 out of 8, which simplifies down to 1 out of 4. So 25% of the time when you toss 3 coins, the last 2 will have H's on them. Exactly one head. Here's one, here's one, here's one. So 3 8s. 2 or more heads. So here's one, here's one, here's one, and here's one. That would be 4 out of 8, or 1/2. You guys get how that works? We have a deck of 10 cards numbered 1 through 10. Some are gray and some are white. So the cards numbered, all of those are gray, and 4, 7, and 10 are white. A card is drawn at random. Let X be the event that the card drawn is gray, and let P of X be the probability of X. Let not X be the event that the drawn card is not gray, and let P of not X be the probability of not X. So for each event in the table, check the outcomes that are contained in the event. Then in the last column, enter the probability of the event. So what is the event of X happening? So X is every gray card. So 1, 2, 3, 4, 5, 6, 7 out of 10 is the probability. So my variable X is every time a gray card shows up. And my function P of X is the number of the probability of that happening. Okay? What about not X? So I need to go through and highlight every time that X fails. Or in other words, I'm going to choose just the whites, right? So these are my not X's. So the probability of not X is 3 out of 10. Now, what do you notice about those two fractions? They add to 1, right? So the probability of X happening plus the probability of not X happening is going to be 100%. All right. So 1 minus 3 over 10 is equal to 7 over 10. Okay, so this is not X and this is X, and it's just saying if you know one of them, you automatically know the other one through subtraction. So this is saying the 1 minus P of not X is the same as P of X. Okay. So this is best answered with a Venn diagram. Okay. So one of these circles is a regular 6-sided dice. And one of these circles, nope, sorry. We're rolling a 6-sided dice. One of these circles are all of the numbers that are odd, and one of these circles is all of the numbers where X is less than 4. So I need to place 1, 2, 3, 4, 5, and 6 in this somewhere. Where does 1 go? Where does 1 belong in these two areas? Well, is 1 odd? Yes, so it goes in that circle. Is 1 less than 4? Yes, so it goes in that circle. So where should I place it? Right in the middle. What about 2? 2 just goes on the right side. What about 3? 3 goes in the middle. 4? It doesn't go in any circle, so where do I put it? Just out in space somewhere. 5? 5 goes in the odd circle, and 6 out in space. Okay? So we're going to introduce some probability words that can be a little bit confusing. And the other word is or. And or. So this right here is referred to as the intersection. Right? When two lines cross, the point that they share is called the intersection. So when you have two number sets and they share something, we call that the intersection. And the intersection is described with the word and. Okay? And then these numbers here are called the union. And the union is described with the word or. So the union is everything that shows up in both sets. The intersection is the area that is shared by the two sets. Okay? And in mathematics, these words have special symbols. The symbol for intersection is an upside down, it's kind of a U. It looks like that. And then the symbol for union is the upside down version of that. So it's just a U with these straight sides. So one of them means union and one of them means intersection. Okay? So what is the probability, or no, these are just events. Which events satisfy A and B? So which numbers are in the intersection? Well, it's just 1 and 3. Those are the only numbers that are in A and in B. Okay? What about A or B? That would be any number that you can find in A combined with any number that you can find in B, and there's no sense in writing a number twice. So that would be 1, 2, 3, and 5. Okay? Now, what is a complement? Anybody know what a probability complement is? It's sort of the opposite. So what is event A? Event A would be, that's the odd one, 1, 3, and 5. What is the complement of A? Everything else. Everything that is not a 1, a 3, or a 5. So that would be 2, 4, and 6. We have another word for this. What did we call the complement in the previous problem, maybe 2 problems ago? We called it not B, or not A, right? Okay. All right. A dart hits the square dartboard shown below at a random point. Find the probability that the dart lands in the shaded region. So we know the dart is going to hit somewhere inside that square. And we know that every point is equally likely. So what is the probability that we land inside the circle? Well, we can just calculate the areas. So the area of the square is going to be 18 squared. And the area of the circle is going to be pi times 6 squared. So how do I find the probability of landing inside here? I just divide them. It's sort of like saying I have this many chances to hit the circle, and there are this many chances total. So 3.146 squared, and you have to hit enter on your calculator or put parentheses around that, divided by 18 squared. It's 3.14 times 6 squared divided by 18 squared is 34.8. What does it want? Nearest hundredth. So I got 0.348. So my answer is going to be 0.35. So you have a 35% chance of hitting that circle. Now, if you are actually throwing a dart, is that going to be true? When you're throwing darts, is every point equally likely? Probably not. Yeah. So it doesn't always work out that way. Chances are you're going to miss the square entirely, right? Okay. Whenever you flip more than one coin or you roll more than one dice, I highly recommend you consider them different coins, like a penny and a dime, or a red dice and a blue dice. The reason is, if you're rolling 2 dice, is 12 equal to 21? Well, it depends on what you're doing. If you're playing Monopoly and you roll 2 dice, is 12 any different than 21? No, because in both cases, you move 3 spaces. Right? But in probability, is 12 a different option than 21? Yes. So I like to think of it as a blue dice and a red dice. Is that the same number? No. Which means we have to count them separately. So, imagine that such a dice is rolled twice in succession and the face value of the 2 rolls are added together, and then their sum is the outcome. So what could happen? Well, I could get 1, 1, 1, 2, 1, 3, 1, 4, 1, 5, and 1, 6. Right? Or I could get 2, 1, 2, 2. That's a 2. But wait a minute, I already have one of those. So should I write it down? Well, they both add to 3. However, are they both individually possible? Yes. Is rolling a 2 on the blue dice and a 1 on the red dice different than rolling a 1 on the blue dice and a 2 on the red dice? Yes. That is different, so we have to count both of them. So 2, 3, 2, 4, 2, 5, and 2, 6. Okay? And then so on. What is the chance that the sum is greater than 9? Well, I better write the rest of these out. So 3, 1, 3, 2, 3, 3. Oh, 5. All right. So which numbers have a sum that is bigger than 9? Would be those. Sum is greater than 9. So there are 6 of them, and there are 36 possible. 6 by 6 is 36. So 6 out of 36 is 1/6. So 1 out of 6 times your answer will be greater than 9. Okay? What about the sum is not divisible by 3? Well, let's count the times it is divisible by 3. So which ones would be divisible by 3? That one? That one? Oh, I missed. Okay, do you see the pattern? So not B has how many options? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So not B has 12 possibilities. If not B has 12 possibilities, then how many possibilities does B have? That would be 36 minus 12, which is 24. Out of 36 is going to be 2/3. Huh. Could I have done that without any work? Well, a little bit of thinking, but no actual calculations. How many numbers in the list are going to be divisible by 3? A third of them, right? Every third number is divisible by 3, so 1 out of 3 should be divisible by 3. Now, if you had 37 numbers in the list, that would make it a little bit more complicated because it's not a multiple of 3. But 1/3 must be divisible by 3, which means 2/3 must not be divisible by 3. All right, that's it. Get to work.